that in laboratory settings, we rely on containers to demonstrate pressure differences.
Not only laboratory settings, but anywhere. Can you show me a scientific experiment with high pressure next to low pressure without containment, without using the earth, or as your example? Yes or no? Can you show me an example? Yes or no?
No. In practical experiments, a containment boundary is typically needed
Okay.
to
Thank you. Welcome to Flat Earth.
G'day everybody, where's Wally here? Old Dirth, he just can't help himself. Yet again, he has taken a flirf talking point and abused the AI, limited, restricted, hamstrung the AI to get the result that he wanted, and then he nauseatingly took the welcome to Flat Earth victory lap right after he did that. Oh boy. Now the journey to get there is really interesting.
Inside the can, the liquid is under pressure from dissolved carbon dioxide. When you open the can, that pressure is released, causing the gas to escape rapidly and making that characteristic psh sound. The pressure inside the can is indeed higher than the atmospheric pressure in the room.
All right, so if the can didn't have any liquid in it, it just had carbon dioxide or whatever gas at that same pressure, it would equalize as soon as you open a can quickly and violently, correct?
They love that rapidly and violently, don't they? A controlled release never seems to make the short trip across their mind.
So continuing, if we keep lowering the air pressure in the room, the gas will still come out whether we open the can on its side, upside down, right side up. Gravity will play no part in holding the gases in the can, and the lower the air pressure in the room, the greater the discrepancy between the can and the room, the more violently and quicker the exchange will be. Is that correct? Yes or no?
Now, let me stop you there, Dave. You said, will play no part. Now, that's not the same as will play no significant part, is it? You're getting a little bit tricky here already, mate.
Yes, exactly. The orientation of the can doesn't matter because the gas will rush out to equalize the pressure difference. The lower the air pressure in the room, the more dramatic the release of gas from the can. Gravity doesn't play a role in the gas exchange. It's all about the pressure difference.
So what about if we lowered the pressure in the can to, let's just say, 1% atmosphere in the can, 1% of what our normal atmosphere is, but we lowered the room to 0. So the room is a vacuum. It would still violently go out. It wouldn't just sit in the can being held down by gravity. It would equalize into the room. Is that correct?
Yes, that's right. Even if the pressure in the can was very low, like 1% of atmospheric pressure, if the room was a vacuum, 0% atmospheric pressure, the gas would still rush out of the can. The key factor is the difference in pressure. As long as there's a pressure difference, the gas will flow from the higher pressure area, the can, to the lower pressure area, the vacuum. Gravity wouldn't stop that. The gas would escape into the vacuum very quickly.
All right, so now let's reverse it. Now I have let's just say I have a box, which is a vacuum. There's no air. It's a zero pressure, zero gas in the box. And I open it up in a room with regular air pressure. No matter where I open it, side, bottom, top, it doesn't matter. The air in the room will violently fill in to equalize, correct?
Yes, exactly.
All right, so wait, hold on. I don't need a detailed explanation. So...
Oh, Dave, you do need a detailed explanation because, Dave, you're not smart.
So if I lower the air pressure in the room down to 1% atmosphere, it's still going to go into the box, right? Gravity's not going to hold it to the floor. The box, whether I hold it near the ceiling or near the floor, whether I open the top, bottom, or side, if there's 1% atmosphere in the room and 0 in the box, the room will equalize and pull up and go into the box. Yes or no?
Yes, absolutely. Even if the room's pressure is only 1% of normal atmosphere, it's still higher than the vacuum inside the box. That difference in pressure will cause the air to move into the box, regardless of orientation. Gravity won't prevent the air from equalizing, so the air will flow into the box, whether it's on the ceiling, the floor, or the side.
And gravity takes no part in holding the air down. It's the pressure that dictates where the air goes, correct?
Dave, you have an unstated major premise here. You are assuming a small scale, in the order of a few meters, in the same local gravitational field.
Correct. It's the pressure difference that dictates how the air moves.
All right.
Gravity does it.
Yeah, so now, sorry to interrupt again, but is there a way I could have a cubic foot of a vacuum inside of a room where I don't have a container for the vacuum? Can that exist?
Well, at least you stated inside a room, so we know we are not dealing with planetary scales here, are we, Dave?
No, that can't exist. A vacuum is the absence of air. So to maintain a vacuum, you need a physical barrier, like a container, to keep air from rushing in. Without a container, the air in the room will immediately fill that space. So you can't have a cubic foot of vacuum just floating in a room.
What about if we reversed it? If I had a cubic foot of air and the room was a total vacuum, could I have that cubic foot of air without a container?
I do hope the AI makes Dave realise that gas pressure is not a problem that scales well, from micro to the macro.
A container, if the surrounding area was a vacuum, the air would immediately expand and rush out into the vacuum. Without a container, there's nothing to hold that air together, so it would spread out until the pressure equalized.
What if I had that cubic foot of air down on the ground in this vacuum area, this vacuum room, but no container, but it was down near the ground where gravity is the strongest? Would that help?
Oh, Dave, that's so dopey. Gravity is essentially the same at all points within the confines of any room or man-made volume enclosing structure.
No, it wouldn't help. Even near the ground, gravity isn't strong enough to keep a pocket of air together in a vacuum. The air molecules would disperse almost instantly to fill the vacuum. There's no way to keep that cubic foot of air intact without a physical barrier in a vacuum environment.
Is gravity stronger near the ground than it is at a high altitude?
Good question, Dave, and I know that you know the answer already, so let's hear how you wiggle words this one.
Yes, gravity is slightly stronger at ground level than at higher altitudes. The difference is very small, though. The change in gravitational strength over a few thousand feet is minimal. So, while gravity is slightly stronger at sea level than on a mountain, that difference isn't enough to keep air from dispersing in a vacuum.
Okay, now I'm going to review a few of the things that you said and then ask you a question, and I want you to answer them scientifically, without consensus, without reading Wikipedia. I want you to answer them scientifically.
Oh, that was a lot of constraints that you forced on the AI there, Dave. Are you aware of how you are trying to manipulate the science? Of course you are.
So you said gas needs to be contained, needs a container. Gravity does not affect the direction gas goes. It's the pressure difference that dictates where the gas goes. If we had 1% atmosphere and 0, they would equalize up, down, left, or right. You agree with that, and you said gas needs a container, or a vacuum needs to be contained if it's surrounded by gas. So we've determined all of that. So the Earth.
The Earth as a whole is not the same as a room on the surface of the Earth, is it? We can't just extrapolate the room and a box to a massive planet with an atmospheric gradient. Is that correct? Now, if you don't state something along these lines, Dave, then you're a manipulator or dumb or...
We're told is a globe surrounded by high-pressure air adjacent to the void/vacuum of space. How come the air doesn't equalize into space?
High pressure adjacent to the vacuum of space. Wow, Dave, just jump right into the meme of maximum flurf derp, would you, mate?
That's a big and interesting question.
Big and interesting question, much like walking across a paddock where we keep the stud bull and mindful not to step in the steaming piles of big and interesting questions.
In the standard scientific model, Earth's atmosphere is held in place by gravity.
Stop. You said gravity does not hold air down.
Stop. Why, Dave? You're about to have it explained to you like you're 5.
And at high altitudes, the gravity is even less than it is on ground. How could the gravity not pull the air into space? You can tell me you don't know and it's an anomaly and you don't have an answer, but don't lie.
Don't lie? AI doesn't lie, Dave. That's your wheelhouse.
I understand what you're getting at. Gravity does hold the atmosphere to Earth. Even though gravity decreases slightly with altitude, it's still strong enough to keep the atmosphere from escaping into space. The atmosphere gradually thins out with altitude, creating a pressure gradient. This is why we have a thick atmosphere at the surface and it becomes very thin at higher altitudes.
I understand why you say that there's a pressure gradient. That's why I asked you earlier if the room had 1% atmosphere, which would represent the very top of our pressure gradient adjacent to a void. If I had a box that represented outer space, which is a vacuum, you said no matter what, the air would equalize up and away from gravity into it. But now you're claiming that gravity holds it down. Do you see the discrepancy here? Do you see what you're doing?
Oh, we all see what the AI is trying to do, Dave. Do you see what you are doing? Do you see, Dave?
I see your point. The analogy with the room and box is simplified. In reality, Earth's atmosphere is a large, continuous system.
So different to a box in a room. Okay, Dave?
Gravity acts on the entire atmosphere, creating a pressure gradient from the surface all the way up to the edge of space. The atmosphere doesn't just sit next to a vacuum, it gradually transitions into it.
Oh, very nicely worded, and as such, Dave is not going to like it one little bit.
So you're telling me now if I took that box of, I have a box of no pressure, of a vacuum, and I brought it up to 10,000 feet and opened it, it would suck air up and away from gravity. If I brought it up to 100,000 feet and opened it, it would suck the air up and away from gravity. If I took it to the very top of the atmosphere, all of a sudden it would stop equalizing because earlier you said no matter what, if there's any difference in pressure, the pressure will equalize. Don't make up shit when you're answering.
Look, Dave, I can see you're really upset about this.
You're right that the principle of pressure equalization applies at any altitude. If you have a vacuum container and open it, air will move to fill that vacuum regardless of direction. The reason Earth's atmosphere doesn't simply vanish into space is that gravity continuously acts on all the air molecules, keeping them bound to Earth. The atmosphere thins gradually as altitude increases, forming a gradient. But it's not a hard boundary. It's a gradual transition where molecular motion and gravity are in balance. That balance is why the atmosphere doesn't just rush off into space.
You're contradicting what you said earlier. You said no matter what the difference in the vacuum to the pressure in the room, whether it's 1% or even less, that it would equalize. But now you're saying there's a magic line where the vacuum will not equalize. What is that percentage? What percentage atmosphere is it where it will stop equalizing?
I never said there was a line. AI said there is a gradient.
There isn't a specific magic line or percentage.
Because you're making it up. That's why there's not a specific magic line.
I honestly think you ought to sit down calmly. Take a stress pill and think things over.
Will you admit that to have air pressure, you need a container because the air needs to push off of something. I could have a tall tank of oxygen or hydrogen or propane, and if it's half full, the bottom will be liquid, the middle will be a thicker gas, the top will be a thinner gas. There's a pressure gradient. And if I made that tank 100 feet tall or 1,000 feet tall, it would get thinner and thinner and thinner. And then if I put a hole in it anywhere, all of the gas would instantly equalize with the outside air, especially if it was in a vacuum. So you need a container to have pressure, and a pressure gradient is necessary to have a container.
Dave, I just want to say, what the hell, man? You've got yourself bamboozled and you're repeating a circular reference as if it's science. Oh boy, what a wicked web we weave. And I can't wait to hear what the AI thinks of you now.
That's correct, right?
A pressure gradient can form naturally due to gravity without.
What would it be pushing off of? What would the pressure needs to be pushing off of its container? What is the pressure of the atmosphere pushing off of? And if you say gravity, you're a liar.
Well, Dave, how about below? The atmosphere is pushing off the ground, okay. And to the north and to the south and to the east and to the west. And in fact, in all 360-degree directions around you, the atmosphere is pushing off, well, the atmospheric column right next to you. So that just leaves one direction left, up. The atmo at 1 meter is pushing off the atmo at 2 meters and vice versa. The weight of the column of atmo above is exactly matching the pressure the atmo at 1 meter is experiencing. It's all very easy.
In the atmosphere, the pressure at any point is due to the weight of the air above it.
Hey, that's what I said. You really are smart, aren't you, ChatGPT?
Each layer of air is compressed by the layers above it, creating a pressure gradient. That gradient is a result of the gravitational pull.
You know it, I know it. Anybody want to have a guess who doesn't know it?
Acting on the entire
You said that gravity does not affect the gas at all. It has to do with pressure. But now you're invoking that gravity on a large scale does hold gas down.
Yes, by your own words, Dave. Gravity on large scales, like planetary scales, not just in a box in a cupboard with a fox.
Where we can physically demonstrate with boxes of air and boxes of vacuums that gravity takes no part in it. But on a planetary scale, all of a sudden the rules change?
You're not just whistling Dixie there, Dave. Yes, planetary scale is very different to your Pandora's box of gas, Dave.
There's no confusion here.
Yes, there is confusion here, and it's you, Dave. All you.
You're just making up crap to defend the globe model, when in fact, the fact that a flat Earth model with an enclosed atmosphere would have a pressure gradient, it would contain our air, and it would make more sense.
Really, Dave? A pressure gradient on a domed Earth? Have you sat down and thought about that, Dave? Now, Flatsoid tried this one, and he failed spectacularly. You're not going to be any better. So here's what you're saying, Dave. There is a dome to contain the atmospheric pressure. But there is also a pressure gradient that we have measured all the way up to 38 kilometers above the surface, thanks to Mr. Sensible and his MAGE balloon project. And the pressure at that height before the dome was just 0.2% of the 760 torr at the surface. So already essentially a vacuum. Now here's the fail, Dave. So why do you need a dome again? To contain that vacuum. Yeah? You better prevent that vacuum from mixing with the nothingness of the vacuum of space. What a spectacular fail, Dave. A vacuum inside the Narnia dome and the vacuum outside means no dome needed at all. Oh, Wally, you mong. That white is not hydrogen. The white is the talcum powder from the inside of the latex balloon to stop it sticking together. But actually, it doesn't really change anything. So the talcum powder should also be moved outwards with the expanding hydrogen, which didn't seem to expand very much. Oh, and by the way, the latex balloons, they do rupture at the speed of sound. This is so well cool. Thanks, Mr. Sensible. Dave, I would love to know, why is that not instantly dissipating into this near vacuum of space? Is it because this near vacuum of space is only 2 torr? Maybe. At 0.3% of normal atmospheric pressure, mate, I reckon we're almost at a perfect vacuum by this stage.
So just answer this. If the Earth is a globe with high pressure air adjacent to a void, that's model number 1, the globe model. Model number 2 is the Earth is flat, it's enclosed with a pressure gradient. Which one takes less leaps of faith and has more scientific evidence towards it? Which one?
The latter one, Dave. It requires you to imagine there is a dome that has never been seen, heard, tasted, smelt, felt, measured, or bumped into, ever, versus a model with atmosphere that gradually thins from sea level to the vacuum of space. Now, we saw it out the window of the Blue Origin NS-31 with Katy Perry. The sky was black, as they were above the majority of the atmosphere.
Look at the black.
Look at that view. Look at the view.
God.
Oh, it's unbelievable. Holy.
Moly. I love the dark.
Look at the view, man.
And how do we know that there was a vacuum outside the capsule? Well, that's easy. As it was in free fall, it was accelerating at g, 9.8 meters per second. But right about that time they buckled in again, the capsule was starting to encounter the atmosphere, and you could hear it outside. You could see that the microgravity was stopping as there was now wind resistance. So now no longer in 0 G.
Pick one.
Mine, ChatGPT, pick the globe. Come on.
The standard scientific model of a spherical Earth with an atmosphere held by gravity is supported by extensive evidence and well-established...
There's no extensive evidence. There's no well-established. I'm asking you now, with all of the information that you told me, all of the experiments that we just discussed, which one makes more scientific sense? Forget whether the Earth is flat or a globe. Which one explains the containment of air on Earth? The flat Earth model or the globe model?
Well, Dave, just how much do you want to constrain the AI? Why do all this embarrassing gaming the system, Dave? Just come out and say, repeat after me, the Earth is flat. Just do that already.
Which one scientifically has more evidence showing that that makes more sense? Which one, flat or globe?
Make up your mind, Dave. Do you want the AI to forget everything factual, or do you want it to answer scientifically using established facts?
The scientific consensus...
I don't care about scientific consensus. Consensus is not science. Consensus is just consensus.
Forget scientific consensus? What good has scientific consensus ever done for us? Well, apart from the roads and the wine, that goes without saying.
Right? So which one has more scientific evidence, considering all of the experiments that we just discussed? Which one? A flat Earth with a dome over us containing the air, giving us our pressure gradient inside the container, or a globe where gravity is holding the air down adjacent to a Torr 17 vacuum?
Torr 17 vacuum? Come on, Dave. You've been denying this science long enough. You can deny the correct science in your sleep. You know it's deep space vacuum of 1 by 10 raised to the power of negative 17. How are you ever going to sound smart if you keep saying stuff so incredibly dumb?
Right? Which one makes more sense?
From a scientific standpoint, the model of a spherical Earth with gravity holding the atmosphere is supported by a vast array of evidence and
What evidence? What evidence do you have? Because we just did a whole bunch of experiments and you admitted that gravity does not hold it down. But forget whether the Earth is flat or a globe. Take that off the plate.
Dave is getting desperate for a win now. He's getting tired of being pummeled in the corner by the AI.
If we were looking at it just as science, we said, okay, we got a ball in a vacuum with high pressure air on the outside that's not contained, or we have a flat Earth with an enclosure, a dome that can hold pressure, and it has a pressure gradient. Which one makes more sense?
Still the globe, Dave. It's still the only thing making sense here. Your dome model is shot, Dave.
In a purely hypothetical scenario...
Wow, the artificial intelligence is so much smarter than the actual idiot. Dave, you hear that? Purely hypothetically speaking. So magic is allowed here, Dave.
Where we consider only the mechanics of containing a gas, a closed container would make it easier to understand how to maintain pressure gradients. However...
Oh, brilliant. The AI is going to circle back and shut you down, Dave, even with your Narnia Land fantasy allowances.
When considering Earth, extensive observations of atmospheric behavior, satellite data, and physical...
Stop it. You're invoking satellites. You're invoking stuff that you know nothing about, that you have no evidence of. We're just looking at gas laws. We're looking at containment of gas. We're looking at experiments that we can do. Take boxes of air, boxes of a vacuum, and we could see what the air does. Using those experiments, you have to admit that the flat Earth model, hypothetically, makes more sense than the globe. Would you agree?
So, Dave, even you are invoking the hypothetical and constraining to small scale, not planetary scale. Getting desperate much now, aren't we, Dave?
I understand your perspective. In a simplified scenario focusing only on gas laws and containment, a closed system would make the concept of pressure gradients easier to visualize.
There you are, Dave. Happy now? AI isn't, however.
However, the actual behavior of Earth's atmosphere is explained by a combination of factors, including gravity and the large...
You said that gravity does not affect the gas. So you just admitted that a closed system does make more sense. Is that correct?
Way to not listen, Dave. Now it's time to demand your victory, hey, Dave?
In a simplified scenario focused only on gas laws and containment, a closed system can be easier to understand in terms of how pressure...
A closed system is easier to understand because it makes more sense. A globe with a high pressure system adjacent to a void, you have to take leaps of faith and and consensus and just assumptions that you cannot test. You cannot show me an example of gas uncontained. You can only say, we've known it's tested.
Yes, it's tested, Dave. Good on you for shooting yourself in the foot with that one.
You can, but you cannot show me an example of gas uncontained without reifying your example by using the Earth as an example. Can you show me an example of high pressure next to low pressure without containment, without using the Earth?
Dave, this conversation can serve no purpose anymore. Goodbye.
It's true that in laboratory settings, we rely on containers to demonstrate pressure differences.
Not only laboratory settings, but anywhere. Can you show me a scientific experiment with high pressure next to low pressure without containment, without using the Earth, or as your example? Yes or no? Can you show me an example? Yes or no?
No. In practical experiments, a containment boundary is typically needed
Okay.
to demonstrate.
Thank you. Welcome to Flat Earth.
Ouch, you sounded really disappointed there, Dave, and yet you still took the victory lap, even after all of that. Hey Dave, the AI says that these are yours and that I should hand them to you. This leaves me wondering why you're still uploading these massive fail videos. I wish I could ask you that, Dave. I wish I could ask Dave the following. DITRH, why are you uploading these videos where you are the actual idiot and the artificial intelligence is schooling you so hard? Would anyone who's not banned by DITRH feel like popping over and asking him? He can use the exercise in deleting comments and blocking people. Thanks, guys.